Hi, welcome! In this video we're going to talk about circular motion. If there is no net force applied to an object, like a ball, it will stay still or move with constant speed. If something, like the wind from a fan, applies a force to the ball, it will change the velocity. If the force is parallel to the movement, the ball will slow down or accelerate, and if it is perpendicular, it will deflect. There is a special case, circular motion. In this case, the ball moves in a circular trajectory and feels a perpendicular force, called centripetal force, in every moment. Near circular motion can be found in space, for example, the Moon around the Earth. The gravitational attraction between Earth and the Moon makes the Moon orbit around the Earth in an almost circular trajectory, making a full turn in about 28 days. The same happens with Earth and the Sun. Due to Sun's gravity, the Earth travels around the Sun in an almost circular orbit about once per year. And the rest of the planets of the solar system, like Mars, Saturn, Jupiter and the others, also follow this kind of trajectory. We want to see what parameters affect the forces involved in a circular motion. For a given object, if we have a different speed, the force may be different, and can also change if we have changed the radius of the movement. This force is important because if it is too large, the string could break or our hands may get tired. Well, we could spend several hours trying to calculate equations of the circular motion, but instead of doing that, let's better do an experiment. For our experiments, we're going to use a pendulum. When it is still and only hanging, the string tension is equal to the ball's weight. Now, if we push it sideways, there is an additional force. The string tension is now equal to the weight plus the finger force. The angle of deflection of the pendulum gives us an idea of the magnitude of the lateral force. For small angles, the angle is about proportional to the transfer force-weight ratio. We put two pendulums in a car. One has a wooden ball, and the other has a very light pinball ball. We're going to go around different roundabouts at different speeds, and see what happens. Here, we are driving in the roundabout at 35 miles per hour. As you can see, the balls are being pushed sideways to the right. That's because an inwards force to the left is required for circular movement around the roundabout. The sum of the string tension and the weight gives that force to the ball. Oh, let's see different cases. Here, we're in a big roundabout at 35 miles per hour. Both balls have the same deflection. Here, we're in the same big roundabout at 25 miles per hour. The deflection of the balls is smaller than in the previous case. Now, we're in a smaller roundabout at 17 miles per hour. The deflection is roughly the same as in the first case. Finally, we're in the small roundabout at 10 miles per hour. The deflection is very small. From these examples, we can draw some conclusions. First, the balls always have the same deflection. That means that the ratio centripetal force to weight is the same. In other words, the centripetal force is proportional to the mass of the ball. Also, at higher speeds, the deflection is larger. Thus, higher speeds require higher force. Finally, in a smaller roundabout at low velocity, we get about the same deflection as in the big roundabout at 35 miles per hour. That means that the smaller radius also require higher force. The equation of centripetal force reflects this. Force is equal to mass times velocity squared, divided by the radius. Well, this was fun, but enough hard work for today. Let's better go to the park and relax a bit. Oh no! Circular motion again!